Emma Aryee is a PhD student at University of Saskatchewan in Saskatoon. She's working with Professor Delay, who spent some time on sabbatical at our center. The title of her talk is Synthesis and Characterization of CNHs for Hydrotreating of Gas Oils. And the co-authors are Professor Delay, John Aryee, and John Aryee of Syncrude Canada and Midland.
Good morning, everyone. So I'd like to thank the Division of Energy and Fuel for giving us this opportunity to present our work. So my presentation, the outline of my presentation begins with an introduction, which will be followed by the literature review, and then I'll talk about the research, which includes knowledge gas, hypothesis, and objectives. This will be followed by the experimental method, results and discussion, summary and conclusion, and then I'll acknowledge our funding sources. So, as introduction, hydrotreating can be described as an upgrading process whereby crude and petroleum feedstocks are treated with hydrogen in the presence of the catalyst at high temperatures and moderate pressures to produce products containing low levels of sulfur, nitrogen, aromatics, and metals. This table shows a typical composition of light gas oil and heavy gas oil. From this table, one could see that the sulfur, nitrogen, and aromatic of light gas oil are normally lower than that of heavy gas oil. Any of these feedstocks can be hydrotreated by going through two main reaction pathways. That is hydropurification, which involves the removal of heteroatoms such as sulfur, nitrogen, oxygen, and vanadium, and then hydroconversion, which involves a change in molecular weight and structure of the organic molecule, such as hydrogenation and isomerization. So, environmental regulations regarding the quality of fuel and subsequent emissions from this fuel is one of the driving factors for hydrotreating. In USA, the current limit of 15 ppm. In USA and Canada, the current limit of 15 ppm was set in 2006. For EU and Japan, the current limit of 10 ppm was set in 2009 and 2007 respectively. With such stringent regulations in place, with such stringent air quality limits are in place, as legislation becomes tighter and tighter, the amount of sulfur in the environment is supposed to be minimized. And this controls stock emissions, which is one of the environmental problems being experienced in these different countries. So some of the reasons for upgrading is to meet tighter for companies or transportation industry to help them meet tighter regulations or stringent product quality requirements, and then to curb environmental problems. A hydrotreating catalyst normally contains of a support such as gamma, alumina, and titanium. It also has active metals like molybdenum and tungsten, and then small amounts of promoters are also added to improve the selectivity, accessibility, stability of the catalyst. So this table shows the typical physical properties exhibited by a hydrotreating catalyst. High surface area of 150 or more is important because it allows the active species to be well dispersed. And then the pore volume within this range, 0.5 to 1, is also important because it allows the capacity for metal deposition. Average pore diameter is within 7.5 to 25 nanometers. Example for HDS involving smaller molecules, an optimal diameter of 10 nanometers is important. So the crashing strength is usually between 28 to 138 kilopascal. And then this crashing strength is also important because if you consider industrial reactors, you don't want the catalyst bed to break. And then once you are within this crashing strength, like you prevent the formation of fines, like catalyst fines, which will increase pressure draw. Normally, cobalt and nickel weight percent are in this range 3 to 8. And then we have molybdenum and tungsten between 10 to 30%. So in industry, the traditional support is gamma alumina. But the problem with gamma alumina is that during the catalyst preparation stage, a strong chemical interaction occurs between the support and the metallic precursor. So this prevents the metallic precursor oxide from being totally sulfated. Hence, in order to circumvent the problem, carbon support has been used as an alternative, and we are considering the use of carbon nanotubes such as CNTs and carbon nanotubes, So, talking about the literature review, carbon nanotubes and carbon nanotubes belong to the carbon allotrope family. Other carbon allotropes are diamond and graphite. For diamond, the hybridization is normally sp3, but graphite, carbon nanotubes, and carbon nanotubes has sp2 hybridization. Talking about the geometry of diamond is normally tetrahedral, whereas carbon nanotubes, and graphite has the hexagonal geometry. Carbon nanotubes normally exist as single-wall carbon nanotubes, and is made up of cone-shaped sheets with cone diameter varying from 1 to 2 nanometers at the tip to 4 to 5 nanometers at the wide area. The length of each individual horn is between 40 to 50 nanometers, and then these horns aggregate to form a spherical group which is about 50 to 100 nanometers. The distance between the adjacent horns are between 0.4, and then initially the pore volume is between 0.47 to 1.05, but this could be improved further by oxidation treatment. Also, the specific surface area falls within 50 to 500 meters square per gram. This could also be improved upon oxidation or acid treatment. The cost time distribution is normally bimodal, but with acid treatment, you end up getting mesoporous pore diameter. This figure shows CEM micrographs of the sample, and normally we have the data-like and then the bad-like. The difference between the two is that with the data-like, the horns protrude from the tip of the surface and are clearly visible. But with the bad-like, the horns are really short and then are not clearly visible as compared to the data-like. Production of carbon nanotubes by the Strand method starts with an initiation of an arc between two graphite spheroids placed end to end and separated by a distance of about 1 millimeter after being contacted with a DC power supply. This produces a high temperature at the arc zone where most materials like carbon sublimate. So this, from literature, arc currents of 25 to 120 amps have been used, and then the arc voltages are between 20 to 40 volts. Once the carbon nanotubes have been formed, produced, modification of the surface properties could be done by liquid oxidation. And then the literature result from this shows that with 70% acid treatment for 15 minutes, the surface area improved from 500 to 1,000 to at 25 degrees Celsius and 130 degrees Celsius. Modification introduced functional groups on the surface of the carbon nanotubes like carbonyl groups or carboxylic acid groups. So the reason why we are considering carbon nanotubes as a support for our hydrotreatment is that catalytic activities should be greatly enhanced due to the high purity of carbon nanotubes. There are rough external surfaces to also enable the deposition of metals, and then there's also greater surface activities due to partialization. Also, the higher metaporosity of carbon nanotubes is really important in hydrotreatment. And the extremely high surface area is also an advantage for using carbon nanotubes. So talking about my research, the knowledge gap associated with the research is that there is lack of information about the optimization of carbon nanotubes production, and the application of carbon nanotubes as a catalyst support for hydrotreating activity studies is not reported in the open literature. There is also no known information about the metal loading capability and dispersion of carbon nanotubes supported catalysts for hydrotreatment. In terms of hypothesis, we expect that variation of synthesis conditions like the current, voltage, electrode dimension could affect the CNH production in terms of quality, the amount, the type, And the oxidation treatment could create nanowindows and the carbon nanofilms, which would help to eliminate pore blockage and improve the surface area, porosity, and surface properties of the carbon nanofilms. The chemically inert nature of carbon nanofilms materials may reduce the reduction of the strong metal support interaction as compared to gamma alumina. Also, modification of the surface chemistry via functionalization of carbon nanofilms will provide sites for anchorage of the precursor metal ions. The research objective is to develop pneumocatalysts composite on carbon nanofilms for hydrotreating of gas oil derived from Athabasca bitumen. And the sub-objective related to this work is to synthesize and modify the functional properties of carbon nanofilms and to determine the morphology and characteristics of the carbon nanofilms. Going to our experimental methods. So this is the setup that has been built to generate carbon nanofilms. It consists of a DWA flask, DC power supply, ammeter, voltmeter, and then the control box. So this schematic shows the discharge process. In order to generate two graphite rods, anode and cathode rods of high 99% purity has to be submerged in liquid nitrogen contained in the DWA flask. The arc between the anode and the cathode, the 1 mm arc, is maintained by using the control box, which automatically adjusts the motor fuse screw as the anode side gets sublimated or consumed. Initially, an arc current of 50 amps was experimented, but this was increased gradually to find the effect of current on the production. And then, depending on the gap and the current being used, arc voltages ranging from 20 to 30 volts were registered on the voltmeter. Thus, the anode dimensions that were used in most parts of the experiment, and then the cathode dimensions too were used. This picture shows the reflection of the arc during the process. So, going through the steps, like initially the anode rod is mounted through the support holder, and then once the process gets, the whole process is submerged in liquid nitrogen, and then after the arc discharge experiment, the remaining unbent rods are weighed in order to calculate the yield. Meanwhile, the product in the DWA flask, which contains like carbon products, is allowed to sit for at least 12 hours to allow the liquid nitrogen to evaporate. Once this happens, the ionized water is added to the product in the DWA flask, and then there is segregation of particles. We have some of the particles in suspension, some floating, and then some at the bottom. Some settle at the bottom. The floating and suspended particles are normally carbon nanofilms. So these particles are filtered, collected, and dried. The other carbon particles, which are disseminated as OCP samples, are also collected, dried, and so characteristics. In order to evaluate the properties of carbon nanofilms, these techniques were used. BET to evaluate the surface area and then the textural properties. PGA to determine the thermal stability of the carbon nanofilms. PM to investigate the morphology of the and then the pore structure information. SKIR to determine the functional groups present. Raman to determine the quality of the carbon nanofilms, and then investigate characteristic features of the carbon nanofilms. Also, SRD was used to determine crystal structure identification. So, in order to find out, this figure shows the effect of yield based on the different currents. So from this figure, one could see that as the current increased from 50 to 100, there was a steady increase in the yield of carbon nanofilms up to 70. Beyond from 80 to 100, there was no appreciable yield increase in the yield. Also, when you look at the production rate for carbon nanofilms from 50 to 70 was quite very low, like 0.03 grams per hour. However, when the current increased from 80 to 100, there was an increase in the production rate. But this increase too was not too substantial as you vary the current from 80, 90 to 100. In talking about the system information, like increasing the current results in a decrease in the liquid nitrogen consumption. This is because with an increase in current, there's an increase in the amount of carbon atoms that are sublimated from the surface of the atom. So as this process is enhanced, the liquid nitrogen consumption reduces, and then the process duration also reduces. In order to find out the electrode rod dimensions, at the fixed current of 90 amps, this length of rod were investigated. And then this is the weight of the rod, the equivalent weight of the rod depending on the length. From this column, you can see that the weight of the carbon nanotubes produced did not vary so much after using the different dimensions. However, the process duration decreased with lesser amount of rod. So based on this insignificant change in the weight, it therefore called for system modification. So we have to modify our system by including baffles. The internal diameter of these two baffles used were 4 millimeter and 8 millimeter. And then we also have to extend the length of our rod so that we give more space for the gas to condense on the surface of the Eva flask. After the system modification, we made a rerun of the current, like using 80, 90, and 100 currents. We had to rerun them to see if our yield would be affected by the system modification. And then from our results, we realized that the maximum yield of about 2.5% was realized upon using 90 pounds. And then looking at the production rate to a maximum production rate of 0.13 was observed at 90 amps. So in order to investigate the effect of yield on the effect of time on the yield of carbon nanotubes, at a fixed current of 90 amps, we investigated different times from 10 to 50 minutes. And then with this result, you can see that the maximum yield was observed at 30 minutes. So we looking at the production too, at 30 minutes we had about 0.1 grams of carbon nanotubes. As we increase the time, you expect that the amount of carbon nanotubes will double or triple, but this doesn't happen because of the extreme turbulence in the system and then the evaporation of gas bubbles, you end up losing lots of particles in the process. So all the results on the yield in the previous slide were based on 1 Eva flask. So in order to further improve our production, we had to use 6 Eva flasks and then run the experiment for 30 minutes per flask. After the carbon nanotubes had been synthesized, we functionalized our samples by employing the liquid oxidation method, and then we used 30% of H2O3 and the reflux for 1 to 5 hours at 110 degrees. Functionalized samples in further slides will be denoted by 90 ounce carbon nanotubes functionalized for 30 minutes, and then we have 90 ounce carbon nanotubes functionalized for 4 hours. So this is the TEM micrographs of the prepared carbon nanotube sample. These are 90 amps, and the aggregate diameter is about 100 nanometers. And then zoom on the particle. You can see the data with the horn protruding from the surface. Also, this 8 amps carbon nanotube shows aggregate diameter ranging from 50 to 80 nanometers. So for the functionalized carbon nanotube sample, which were produced at 90 amps, these are TEM images for a time duration of 1 hour acid treatment, and then the SPR results of the carbon nanotube sample, and then the orange one is the description of 90 amps carbon nanotube. All the SPR sample shows CC stretching bands in the range of 1,330 to 1,350. However, with the partialized acid-treated samples, like the presence of carboxylic acid groups were observed in the range of 1790 to 1824. So with partialization, we were able to introduce carboxylic acid groups on the carbon nanocons support. Raman spectroscopy of the carbon nanocons also shown in this figure, and all the Raman analysis showed prominent bands, that is D and G bands. The D band is reflective of the disorderliness in the graphite structure, and then the G band is representative of the sp2 stretching banding for graphite. Also for 50 and 60 amps, like the ID to IG ratio was about 0.9, and then almost all the samples have some amount of defects. Defects in carbon nanocons is common because, like, even though it's hexagonal, like the 5-member ring at the tip is hexagonal, and then that creates defects. Like the 5-member hexagon ring, the 5-member ring on the tip creates the defects in carbon nanocons, so it's usual to see defects in carbon nanocons. Also, looking at the functionalized, this is the Raman spectroscopy of the functionalized samples. So, with functionalization, you extend holes or nano windows on the carbon nanocons, and these nano windows are also termed as defects. So, once the functionalization is increased, we observe optimum functionalization of 30 minutes. The ID to IG ratio increased, which was 1.41, and therefore this concludes that, like, there were defects, there were nano windows in the, and then some pores have been opened, which is beneficial in hydrotreating reaction. This is the typical hydrotreater that's used in our lab. So we have the feed and then the hydrogen coming from the top, and then they go through the reactor in the downward flow. Upon contacting with the acid sulfur catalyst, metal sulfur catalyst, the hydrogen and the oil react to form saturated hydrocarbons and then ammonia, H2S, and free metals. The reactor effluent is passed through the scrubber to take away the ammonia, and then the resulting effluent goes through the high pressure separator. Once it gets here, like the H2S, the H2S gas goes through a scrubber, is absorbed through the sodium hydroxide in the scrubber, and then the effluent from this high pressure, the liquid part of the product, is passed through a striper to take away the nitrogen, to remove some of the nitrogen, and then the remaining product is collected and then analyzed for NS and other analysis. So this is a typical experimental round for LGU. Right? There is sulfidation for 2 days sulfidation, and then it goes through a pre-coating period where we stabilize the activity of the catalyst, and then we conduct all our experiments. Currently, we are doing some LGO rounds with 2.5% of nickel and 13% of molybdenum. And then the catalyst was calcined at 450 degrees Celsius for 5 hours with argon gas. The reactor pressure is used as 13, but we are varying to find out the effect of the pressure. And then at the moment we are conducting our runs with an LHSV. Our convention results are not present right now, so talking about the summary and conclusion, carbon nanocons can be produced on a laboratory scale using the submerged arc and liquid nitrogen method. Then the yield for carbon nanocons produced at the various currents investigated were no more than 3%. Also, the design of the carbon nanocons have an impact on the yield and production, even though the increasing in current do affect the production. The design of the setup is also important. The optimal carbon nanocon support could be produced at 90 amps for 30 minutes, and then functionalized with 30% of HNO3 for 30 minutes. Also, BET measurements showed that carbon nanocons exhibit mesoporous diameters Visualization could also improve the textural properties. The Raman spectroscopy for all our samples shows the prominent DNG band occurring between this ring, and then the loss of carbon nanopores particles is always a challenge, and therefore we always get low yield of carbon nanopores. So, in acknowledgement, I would like to thank the University of Saskatchewan for funding, and then the Symposium Canada Limited and NSEC for funding. These are some of the references. Any questions?
Amazing to see how much the VET method is still being used today. Any questions?
I understand you have carbon nanotube, carbon nanobone, carbon and graphite, graphite fibers. Why you particularly choose a carbon nanobone? I understand the bone morphology is difficult to obtain, and in future if you talk about a large scale production, I'm not quite sure it is the right way to go.
Yeah, so we chose carbon nano because carbon nanotubes have been experimented in our lab, and then with carbon nanobones, so we are able to improve the surface area and other textural properties further, which is important in hydrotreating reaction.
Surface area is not important in hydrotreating catalysis. Four sides and four values. I was saying surface area really is not that important in hydrotreating catalysis. The four sides of the support.
Yeah, so with the power volume too, we are able to improve it about functionalization. Like carbon nanobones, you could get like 0.7.
Same thing with aluminum.
But like compared to alumina, with carbon nanobones, we are able to eliminate the support interaction between the chemical interaction between the support, and then we are able to eliminate it because carbon is like in a.
On the other hand, you hydrotreating, you might generate other hydrocarbons because you are using carbon. So as you mentioned in the last one, the being lost is a big issue.
Yeah, like in synthesizing the carbon nanobones, like there are lots of particles during the process. We lose particles during the evaporation of it, like as you are forming the particles, as you are synthesizing the particles using the atmosphere, there's a lot of turbulence, you lose particles through that. There's a lot of evaporation, you lose particles like.
So what you're saying is with alumina you lose some of the metal to the support, right? Actually, you need some metal support interaction, I would think, to stabilize the particle size, the metal particle size. And aren't you you're actually creating some metal support interaction by functionalizing the carbon nanotubes in order to stabilize the particle, right?
Yeah.
So really the benefit is what you're saying is that you're not sacrificing metal to the support. Any other questions?
Comment a little bit about economics. As you mentioned, we have not really studied the economics of production. I think looking at the main application of CNS for the novel support for this particular process, that the economics will only follow this promising. So I think we are more in a preliminary stage. We have not seen any literature showing the CNH as a support for hydroprocessing or even physiotherapy. So I think it's a very novel material. And as you saw, the surface area is about 450 square meter per gram with the average pore diameter is 12.5 nanometer. Even if you put 2.5% nickel and 15% moly on this material, so it's quite promising.
Yeah, from all the fundamental study, I don't have any objection. It's really nice.
What is the mechanical stability? I mean, you have these individual rods, and the pointed area is on towards the outside. So what is the mechanical stability? And normally when you have spherical carbons, which is very desirable, which is great, but they have these pointed spots at the outside. How well do they pack?
Actually, they are basically one particle, as Emma said, is about 100 nanometer diameter. When you do the acid treatment, like put through 30% nitric acid at 110 degrees C for 1 to 5 hours, so it basically opens the tips so that you can put the metals inside for catalysis. So the tips are that you see is just before the dilute acid treatment, but after the treatment there are no tips. It basically opens up for catalysis or for metal deposition, but they kind of stay together. But if you put, if you do the hydro treatment for longer period of time, it will probably crumble down to it's not anymore holding on to the same pattern as you saw in one of the TA picture.
Let's thank Emma once again and all those people.